Hello, my name is Ambrose Finnerty, and I'm the DSP Technical Marketing Manager at Xilinx. Thank you for tuning into this quick take video outlining how to target the Squaring-MUX functionality introduced in the UltraScale architecture's DSP48E2 slice to help improve resource utilization and performance. First, let's quickly review the 7 series DSP48E1 slice and some enhancements in the UltraScale DSP48E2 slice. In 7 series, the DSP48E1 had a 25 by 18-bit multiplier with a 25-bit pre-add. Now in UltraScale, the DSP48E2 slice has a 27 by 18-bit multiplier and a 27-bit pre-add. We also added a wide MUX product feedback to facilitate an additional accumulate in the DSP slice, which was not possible previously. The DSP48E2 slice also has a new Squaring-MUX, which allows for the output of the pre-adder to be squared. That is, d plus or minus a to be squared, or d plus or minus b to be squared. Squaring is one of the fundamental operations widely used in digital signal processing. It has been added to improve efficiency and reduce resources, particularly in video applications when looking at magnitudes, and also for video processing. For the purpose of highlighting this Squaring-MUX feature, I'll use a simple squared difference accumulate function. That is, the sum of a minus b to be squared over a value of n. I'll use the Vivado high-level synthesis tool, HLS, now free in Vivado HLS, to show the improvements from 7 series to UltraScale. This function consists of a difference between two inputs, a and b, the multiplication of the result of that difference, and then an accumulation of the multiplications for n samples, with the final output being the result of n accumulations d out in the example code shown. The pragma is applied for pipelining the design. These 3 calculations can now be done in one DSP48E2 slice. Moving into the Vivado HLS tool with the different squaring project open, you can see in the left-hand Explorer column the source files and solutions associated with the project. I have created 3 solutions to easily show the comparisons between 7 series, UltraScale and UltraScale Plus. The project contains 3 source files: the design itself, and the header file, which is called from within the design file. This file contains the necessary data type definitions used in the C function, that is din_t and dout_t. It also defines the number of iterations of the loop required for each output from the function, in this case 10. This number can be modified as required. Then finally, there is a self-checking C test bench. You will see in this test bench file a reference procedure at the top. Then in the main test bench there is a call to both the reference function and the design under test function. There is some random stimulus generated and applied for the inputs A and B, which are used by both functions. Then finally a comparison is performed on the results of both functions to ensure functionality is correct. To validate the function, you can run the C simulation using the following button on the GUI toolbar. When the simulation completes, the log file for the simulation will automatically open, and as you can see, we achieved the expected results and the test successfully passes. Usually after validating the functionality, one would run the C synthesis for their chosen solution within the project. As I have ran all 3 solutions in this project, it is an easy task to compare the 3 synthesis solutions. To do so, select all 3 solutions using the Control button and then choose Compare Results. The results will auto-populate in the GUI. It can clearly be seen that the K7 solution requires more LUTs than both UltraScale solutions. To understand the reasons for the LUT utilization decrease in the UltraScale architecture versus the 7 series, it is necessary to look at the individual DSP48 equations in each solution. If I open the synthesis report for the Kintex UltraScale Plus solution and take a look at the expression implemented On the DSP48E2 slice, it can clearly be seen that this is a squaring of a subtraction with an addition. If we look at the synthesis report for the Kintex 7 solution, and again view the expression implemented this time on the DSP48E1 slice of the 7 series architecture, it can be seen that no subtraction can occur on the DSP48E1 slice, and it must take place in the FPGA fabric, resulting in a LUT count increase compared to the UltraScale architecture. Finally, to summarize, I will compare the implementations for the 3 architectures. You can see here that the slice and LUT utilization is reduced in the UltraScale architecture by way of using the Squaring-MUX within the DSP48E2 slice. This allows the subtraction to occur in the DSP48E2 pre-adder, and then feeds by way of this MUX the output of the pre-adder to both inputs of the multiplier. In previous architectures, the subtraction needed to take place in the fabric. It can also be seen that the Fmax achieved is greatly improved as one moves from 7 series to UltraScale Plus. With the release of the Vivado HLS software in 2015.4, Vivado HLS is now included in the Vivado software toolset at no extra charge. A high-level productivity design methodology guide, UG1197, was produced and released to coincide with the HLS toolset, and should be reviewed and followed. It is important to note that there are existing, ready-to-use HLS libraries available for some common DSP, video, linear algebra, and math.h functions. These are described in the HLS user guide UG902. The HLS landing page contains an Open Example Project tab, and from there one can find useful design examples and coding styles for reference. Thank you for watching.